All right, this is our fourth set of notes for Chapter 8. In this set of notes, we will talk about PXY phase diagrams. So we've talked about TXY. Now it's time for PXY. In a PXY phase diagram, we hold temperature constant and we plot pressure versus composition. Okay. So it's going to look fairly similar. Okay. Only now in a PXY phase diagram, temperature is fixed. So I plot pressure versus composition, X and Y. It's going to look a little different. So if I look at the two limiting cases again, so in the limit that x1 goes to 0, that's going to correspond to pure component 2, pure decane in this case. Where my phase envelope touches my left axis, that's going to give me the boiling point of pure decane. Okay. And now when we talk about boiling point, it's probably a little different than you've thought about it before. So in our TXY, we said that at this given pressure, boiling point would be the fluid boils at this temperature. Okay, it's the same thing here, only now at this fixed temperature, the fluid boils at this pressure. Okay, it's just something you're not typically don't think about as much. Okay, so where my phase envelope hits my left axis, this would correspond to the bubble point of pure decane. And the limit that x1 goes to 1, this would correspond to the bubble point or boiling point of pure heptane. Okay, so where my phase envelope hits this left axis, that's the bubble point or boiling point of pure decane. So again, now temperature is fixed, so we're thinking about pressure. So that would correspond to, say, PSAT, my pure component saturation pressure. Then same thing here on the right-hand side. This would correspond to the pure component saturation pressure of component 1. Okay, so now let's think about volatility again. Okay. When I'm constructing TXY and PXY phase diagrams, it's customary to plot with respect to the most volatile component. Why? Because in a vapor-liquid separation process, say distillation, my goal is to concentrate the most volatile component in my vapor phase. Okay, so the same is true here. But now when I think about volatility, okay, so in our TXY, when I compared those pure component boiling points, so T's at a given P for my fluids, we said the component at a given pressure with the higher boiling point temperature corresponded to the least volatile component, right? It was harder to boil. When it comes to these pure component vapor pressures, the opposite's true. So the component with the higher pure component vapor pressure is going to be the most volatile species. The one with the lower pure component saturation pressure is going to be my least volatile component, right? So you can think, vapor pressure would be the tendency of that pure component system towards the vapor phase, right? The higher the vapor pressure, the more of those molecules I'll find in the vapor phase, right? So it's going to be more volatile, right? The weaker intermolecular interactions. So my shape changes a little bit here now, and that when I look at my two endpoints, right, it's going to go from low to high, right, when plotted with respect to the most volatile component. Okay. All right. So again, 2 graphs versus 1, we plot pressure versus composition. Okay. So now, temperature is fixed. So if I think about this, okay, if temperature is fixed and I were to decrease the pressure, okay, so if I decrease the pressure of a mixture of two-phase saturation, that's pushing me towards a vapor phase. So now on the bottom or below my phase envelope, I have a vapor. Okay. High pressures favor liquids. I have a liquid in top. Okay. This is my phase envelope. The line separating my liquid from my two-phase is again my bubble line. The line separating my vapor phase from my two-phase is again my dew line. Okay, so I've got my bubble line and dew line just as before. Liquid up top, vapor on the bottom, and two-phase in between. Okay, a characteristic of a system that is behaving ideally is this bubble line is straight. Okay, again, we'll look at exceptions to the rule later on, and mostly when we start to talk about non-idealities in solution. Okay. All right. So now, if I think about distillation, flash distillation drum. Okay, and so the goal is I'm going to start with the liquid. I always essentially start with the liquid. Why? Because if I'm trying to move components around my chemical plant, it's much easier to pump a liquid, right? So how I make something flow is I create a pressure gradient, right? Fluid mechanics. So when it's the case of a liquid, I can add pumps to move my components around my system. If they were gases, I have to deal with compressors, which are going to be much more expensive and not as nice to work with. Okay, and so the general idea now if I think about a flash drum, is I start with a liquid phase, and now I can do two things, right? If I think about my TXY phase diagram, I can increase the pressure to push me towards the two-phase region, or now if I think about my PXY, I could equivalently decrease my pressure. Okay, so in terms of a flash drum, you could either be heating it or you could throttle it, but the goal would be I enter my two-phase mixture, or my drum, where I form a two-phase mixture, a vapor coming off the top and the equilibrium with a liquid coming out the bottom. Okay, so this picture is taken from the book I used in mass transfer. And this screen up here, that corresponds to a demister. And it's just, if your flow rate's say too high, you could entrain liquid droplets within your vapor going out the top. Okay. All right, so what we're going to do is we're going to picture this as a simple diagram for the context of our PXY phase diagram, where the idea is if I start with a feed of composition Z1, right, a liquid feed, I'm going to throttle it, so I'm going to reduce its pressure, so I enter the two-phase region, okay, and so the pressure of the drum will typically be specified, so that coming out the top, I have a vapor in equilibrium with the liquid. All right, so now if I try and picture this flash drum in a PXY, I'm going to start with a liquid, say of composition Z1. Now I'm going to decrease the pressure, so I'm going to decrease the pressure, so I'm going to isothermally throttle my fluid to decrease the pressure to bring it to the two-phase region. In terms of determining the composition of my vapor and the equilibrium with my liquid, once again, if I think about my Gibbs phase rule, if I have a binary system at two-phase coexistence, so for my two-phase region, number of degrees of freedom are 2. Well, temperature is already fixed in my diagram. Temperature is constant throughout. And so next we'll have our criteria of mechanical equilibrium, pressure, and then that's our second independent variable that fixes the state of our system. Okay, so how I find the composition is I draw an isobar. Once again, I read off vapor compositions for my dew line and liquid compositions for my bubble line. Okay, and once again, when we plot with respect to the most volatile component, right, my dew line is going to be to the right of my bubble line, and we get a vapor composition Y that's greater than the feed I started with, which is greater than X. Okay. Example 8.4. So a mixture of heptane and decane at 1.8 bar and 120 degrees C contains 80% by mole heptane. At what pressure should it be flashed to obtain a stream that is 90% rich in heptane? What are the composition of the liquid and the amounts of the two phases? Okay, so if I draw a picture, I have a feed that's 80%, so 0.8 mole fractions heptane. I want a vapor phase coming out that's 90% heptane, so Y is 0.9. I don't know what the liquid is. We're not told what the liquid composition is, but we're given the temperature. So the significance of the temperature here, if I flash back and I'm thinking about a PXY phase diagram, remember temperature is fixed. So in them giving us temperature, that essentially tells us what PXY phase diagram to look at. We're given the composition of my feed. We're given the value of Y coming out. Okay. So in here, okay, so if I think about my feed, okay, and I think about a PXY, this is going to allow me to draw a vertical line up and down in my phase diagram, right? And I know I'm going to lie somewhere on that line, right? My composition of my total system is going to be constant. It's going to remain on that line. But now, within my drum, right, I know I have this temperature 120 degrees C. I know what PXY phase diagram I'm looking at. And I know I have a system at vapor-liquid coexistence at this mole fraction, Y1 is 0.9. Okay? Right, and so, already what I see is if I have a system at two-phase equilibrium and I'm given the temperature and composition, I'm given two intensive independent variables that tells me the state of my system is fixed. So in theory, I should be able to find everything else. Okay? So how I do that is, again, I would start by drawing this vertical line, okay, and Y. Okay, and this could be a little confusing, but you've got to think of this as a closed system. So if I start with a closed box, right, and it has a mole fraction of 0.8 mole fractions of heptane, and I take that and I heat it all the way up to the vapor region, so beyond my dew point, right? My system's closed, so all the moles I started with are still in there, right? They're just now at a much higher pressure, right? Why? Right? Because the molecules want to get away from each other, so they're exerting more force on the boundaries of that box. Okay, but regardless, the mole fraction of that total system is the same. Okay, now in between my bubble point and my dew point, where I have a two-phase mixture, I'm still in a closed box where I have a liquid phase in equilibrium with the vapor phase. Okay, but if I look at the total system, the total number of moles within that system is still constant. The total volume is still the same, right? It's all still the same, right? In terms of that, extensive property, right? So, even when I'm in the two-phase mixture, if I want to calculate the total composition, right, the total composition is exactly the same. What's different are the compositions of the liquid and vapor at equilibrium with each other. Okay, so I start by drawing this vertical line because I know, no matter what for the process, I will be somewhere on this vertical line. Okay. And then the second piece of information we're told is that I'm looking for a mole fraction of a vapor phase mole fraction of 0.9. Okay, and so if I draw that line, okay, what I'm looking at is, I read off vapor compositions for my dew line, so I'm drawing a vertical line at y1 equals 0.9 up to the dew line. Okay, why? Well, now I've specified y. T is already fixed. This entire diagram is drawn at a given t, and so thermodynamic state of my system's fixed. So if I have a system at vapor-liquid coexistence in this vapor phase mole fraction, how I find the liquid is I draw an isobar, right? Because my two phases are at the same pressure. I draw that horizontal line across. Okay, I find where my isobar hits my bubble line. That's going to give me my liquid. Okay, so I'm going to do exactly that. So I draw my horizontal line across. Okay, well, if I bring it all the way over, I see that that corresponds to pressure of approximately 1 bar. And if I want the composition, I just read down from my bubble line. I get a liquid phase mole fraction of 0.5. Okay, cool. And then if you want to know the flow rates, well, we weren't given F, so you can't exactly solve for L and V. You would need to have, say, a basis of what F is. Oftentimes in the book, they're a little confusing. They make it seem like you should be able to calculate L and V, but essentially they're always assuming a basis of F is 1. Okay, but regardless, we could go back and look up our lever rules or do a mass balance. And so the amount liquid is 0.25 relative to the total feed, and amount vapor is 0.75 relative to the total feed. Okay, and these are from when we derived the lever rule, which is nothing more than a mass balance and a component mass balance. Okay, and that's the end of set of notes 4.